All right, class. So the last thing we're going to talk about factors that affect solubility. Let's talk about this to finish up the chapter. Now, here's what I need you to remember, and this is really key when we're talking about this. Factors that affect solubility. What am I talking about? What I'm talking about here, I'm talking about molar solubility X. What I'm not talking about here, I'm not talking about Ksp. Because if you remember, and I need you to remember this, that Ksp is a constant, right? Ksp is a constant, and like any other equilibrium constant is only what? Is only temperature dependent. Only temperature dependent. And I need you to remember this. So because when I talk about factors that affect solubility, everyone goes, well, how come temperature is not one of them? Well, here's the thing. Temperature does affect it, but what temperature does, temperature would affect the Ksp. Ksp is a constant, and like any other equilibrium constant is only temperature dependent. Ksp is only temperature dependent. So I need you to remember that, yeah? Now here what we're talking about, we're not talking about Ksp, we're talking about basically X, molar solubility. And the factors that affect solubility are common ion, pH, and complex ion formation. And I'm going to go over each one by one with you. And you already know the common ion effect, but I'm going to go over it again anyway. So far so good? Okay, so again, I need you to remember this for me, that Ksp is a constant, and like any other equilibrium constant is temperature dependent only, right? It's only temperature dependent. All right, now common ion effect. We've already talked about this a little bit, so you already know. So if I have a salt, I want to just say Ma, okay? And it would break up into M plus and A minus. This is just generic. So these are my common ions. These are my ions, right? Now, you know Le Chatelier principle, that if I add any of these two ions, these are my common ions, because these are the ions I have for this equation. If I add any of these ions to this equation, to this reaction, where would the reaction shift to balance the equilibrium? It would shift to the left. Exactly. So if I add any of these common ion to my reaction, it would have to adjust to balance the equilibrium, to reach equilibrium. So if I add any of this, it would have to shift to the left. You guys are good so far? Okay. So tell me, what is the effect of common ion on solubility? If I have any of these common ion, if I add to the solution, it would have to shift to the left, right? To balance to reach equilibrium again. So what would it be? If it shifts to the left, I'm going to have more of this insoluble salt. So if I have a common ion, what would happen to the solubility? The solubility would go down. We've talked about it a little bit. We're going to do practice problems to make sure you get this down. So far, so good? Okay, beautiful. Now, what are we going to do? Let's do a couple of practice problems. Here are our first practice problem. So what is the concentration of Pb plus 2 ions when PbI2 is dissolved in water? So PbI2 is dissolved in water. Okay. So this is nothing fancy we've never seen before. So PbI2 led to iodide is my solid, my slightly soluble solid, mainly insoluble. So I'm going to write the equilibrium. So far so good. Okay, so PbI2 will break down into Pb plus 2 and 2I minus. And then, of course, don't forget, this is my solid, yeah? So over time, this is going to disappear, and this is going to be my x, and this is going to be my 2x. Do this every time, even if it's an easy problem. Write this down. Write down the equilibrium, and then write down the Ksp expression. So the Ksp would be the concentration of Pb plus 2 times concentration of iodide to the power of 2. Okay, so far so good. All right, is the Ksp given to me? The Ksp is given to me. Ksp is 6.5 times 10 to the minus 9. I don't have the concentration, so I'm going to put X for Pb plus 2 concentration, and iodide is 2X, but again, to the power of 2. I know you know this, but one more time. So here, I don't have the concentration, so for Pb, I want to put X. For iodide, I want to put 2X, but again, you have to follow the formula. It would be to the power of 2. The 2X is just the concentration. All right, beautiful. So a little algebra, this would be 4x cubed. So if I calculate the value for x, what I would get is 1.2 times 10 to the minus 3. That is my molar solubility. So far, so good. Okay, so that's, and again, this is a 1-to-1 ratio for Pb plus 2. So this would be the answer. All right, now that was part A. Let's do part B. What is the concentration of Pb plus 2 ions when PbI2 is dissolved in a solution that is 0.275 molar in calcium iodide? Now, calcium iodide is 100% soluble in water. If you look at the solubility rules, we'll see that it has 100% solubility. So we break up into fully to calcium plus 2 and 2I minus. So you have 100% dissociation, it would fully break up. And I have that in the solution. So far, so good? Okay. Now again, keep your eye on the price. What I'm trying to figure out here is PbI2, right? That hasn't changed. And what I'm going to do, I want to again write down the equilibrium equation for that. Always do this even though you know everything, okay? Now, here's the thing. When I have this solution, and this is what's different from the last problem. The last problem, it was dissolved in water. Now, it's dissolved in a solution that has 0.275 molar in calcium iodide. Okay? Now, what does that mean? What does that mean? So, when I have this PbI2, I also have this calcium iodide in the solution. Well, I know calcium iodide would 100% dissociate, right, into calcium plus and 2I minus. Now, how much calcium is not going to do anything to me? These are my common ion. Calcium is not part of them. So calcium is just floating around there. It's not really going to make not going to affect anything we have because it's not one of my common ion. But how about I minus? I minus is my common ion, right? So it's going to have a common ion effect. Again, calcium is not going to do anything, just floating around. It's not one of my common ion. But hey, I minus, that is one of my common ion. So I have a common ion effect problem here. So far, so good. Now, we have to do a mole ratio. Don't forget the hashtag mole ratio always comes back. So I have 0.275 molar of calcium iodide. When everything fully breaks up, how many moles of iodide am I going to have? You have to do a mole ratio. For 1 mole of calcium iodide, you have 2 moles of I minus, right? Okay, it's a 1-to-2 mole ratio. It's a 1-to-2 mole ratio. So when everything breaks up, because each calcium iodide has 2 iodide. So what I would end up with is 0.550 molar I minus. So far, so good. So when I start this reaction, I have this much iodide already in the solution. So when you have a common ion problem, you can do an ice table, right? With equilibrium, you can do an ice table. So at the beginning, I have none of this, and I have, but what do I have? What I have is I have a 0.550 molar I minus. So far, so good? Okay. Now, what does that mean again? This is same as before, minus x, x, and 2x. Okay. Now, here is going to be my x, and here would be 0.550 minus 2x. Now, I kind of ignored this one altogether. I was writing things down and I decided to ignore them. Why am I ignoring this altogether? Because this is solid. And if this is solid, don't even bother. I started writing things down and I was like, I don't really need that because this is solid. Solid is not part of the equilibrium equation. You knew that. So far, so good? Okay. So again, these are the only ones I care about. This one, we don't need to write it because it's a solid, and solid is not part of the equilibrium equation. All right, so I'm going to do the same as before. We're not going to cut any corner. I know you're probably so good at these right now, and you want to cut corner, but don't. Write down the Ksp expression every time. Okay. Now, again, we're still talking about PBI2, so I've given you the Ksp in part A, so that's the Ksp. Now, again, PB is X. Now, I would be 0.550. Oh, plus. No one said anything. You probably did. I couldn't hear you. Plus 0.2x. So far, so good. Now, again, I have to do it to the power of 2. You guys follow that? Okay. I know you follow that. I'm going to go over it one more time anyway. So again, I didn't really care about this. Solid, not part of the equilibrium constant. You knew we have a common ion effect problem. How did you know that? Because you have this calcium iodide in the solution. You have 100 dissociation and you have I minus. Calcium doesn't mean much. They're not going to do anything for us. I minus. Ooh, that's one of the common ion. That's great. So I have a common ion effect problem. I can do an ice table, I can do an ice table at the beginning. I don't have any of this, but I do have some iodide in there. And then again, we go minus x, and x. Now we plug it into our Ksp expression. So far, so good. Again, instead of I minus concentration, this is what I put in, but I still have to do it to the power of 2. That doesn't change. All right, now what I'm going to do, you're going to like this. I'm going to assume this is 0. Why can I assume this is 0? Because my Ksp value is super, super small. 0.550 is such a big number compared to what this x is going to be, right? 0.550 is so much larger than my Ksp value, so I can assume this is 0. And if I assume this is 0, then the algebra is not bad. Then it would be x, then it would be 0.550 to the power of 2. So far, so good. You guys are following me? Okay. Now I'm going to solve for x. If I solve for x, what I end up getting is 2.1 times 10 to the minus 8. All right. So what did we learn? Mathematically, I wanted to show you what you already knew. We knew that when you have a common ion effect problem, if you have one of the common ion already in the solution, think about Le Chatelier is going to shift to the left, right? Because you add any of these two common ions in here is going to shift to the reactant. What that means is you're going to have more of this insoluble solid. So we expected the common ion effect is going to make the solubility to go down. Is that what we saw? Oh, I hope so. So without the common ion effect, this was my solubility, 1.2 times 10 to the minus 3. Now, with the common ion effect, oh wow, 2.1 times 10 to the minus 8. It went from minus 3 to minus 8. Yeah, much less dissolved, right? Much less dissolved. Again, why is that? Because I had one of the common ions, so it shifts towards the reactant, it shifts to the left. Now I have less dissolved in water. I have less dissolved in water because now I have more of the insoluble solid. Yeah, you guys feeling pretty good about this? Okay, since you're feeling good about this, I'm sure you want to do one more practice problem. Let's do it? Yeah, let's do one more practice problem. Okay, so here is our next practice problem. Pause me, do this, and then unpause me, and we're going to go over it together. So, nickel hydroxide, again, whenever you see these problems, write down the equilibrium. That's the first thing you should do. I'm going to write down the equilibrium. I'm not even going to read the question first. I'm just going to write down the equilibrium. So far, so good. Okay. Now, in this problem, interesting. they give me a pH. Yeah? So what can I do when I have a pH? Here's the thing. What do you have in this problem? What you have in this problem, you have a base, don't you? Yeah. So we have a base in this problem, and they're giving you a pH. They give me a pH. I have a base. So what is the one piece of information I should figure out, and it's going to help me? Is pOH, right? Because I have a base. Let's figure out the pOH. So the pH is 10.72. I have to subtract it from 14. You know how to do that, right? When you do that, you get the pOH, which is 3.28, would be my pOH. Now, this is great because what pOH is, if you remember, pOH is minus log of OH minus concentration. Yeah? And now, right now, you have the pH and you can figure out the OH minus concentration. Now, so the OH minus concentration is going to equal 10 to the minus 3.28. I just want to make sure everyone's on the same page with algebra. If we do that, what we end up getting is 5.2 times 10 to the minus 4. 5.2 times 10 to the minus 4 would be my hydroxide concentration. Okay. Now, I give you the pH. You go, okay, pH, but what I have here, I have a base. So let me figure out the pOH. You have a pOH, which means you can figure out the OH minus concentration. Now, what can you tell me? I can almost hear you saying it. What type of problem is this? This is common ion effect. Why? Because so now you have some hydroxide already in the solution, and hydroxide is one of the common ion that we have. So hydroxide is one of the common ions. So yeah, I have a common ion effect problem. So far, so good. Okay. So I'm not going to worry about, again, the nickel hydroxide here because it's solid. That's not part of the equilibrium. I can still do an ice table, So I don't have any of this common ion, but I have 5.2 times 10 to the minus 4. Okay. Again, the minus x, this is x, and this would be 2x. The same as before, I'm going to write down my Ksp expression. My Ksp would be the concentration of nickel plus 2 times the concentration of hydroxide to the power of 2. You probably got this down by now. All right, so nickel, that would be x. Yeah, that's going to be my x at equilibrium. And hydroxide would be 5.2 times 10 to the minus 4 plus 2x. Let's not make the same mistake here. Times 10 to the minus 4 plus 2x. And to the power of 2. That doesn't change. This one here, this is over here, is the hydroxide concentration. You still have to do it to the power of 2. Can we assume x is 0? You bet. We can assume x is 0 because look at this Ksp. The Ksp is so small. The Ksp is so small. We have 2.0 times 10 to the minus 15. All right, so the Ksp is pretty small. And even though 5.2 times 10 to the minus 4 seems like a small number, is a lot bigger than the Ksp that we have here. This is a lot bigger number than the Ksp. We can assume x is 0. Now, if we do that, then the math just got so much nicer. Then that would be x, and this would be 5.2 times 10 to the minus 4 to the power of 2. If I do that, what I end up getting for x is 7.4 times 10 to the minus 9. That would be my molar solubility of nickel hydroxide. Yeah? Okay. Beautiful job so far. I just want to talk about a couple of side notes, even though you notice, again, common ion effect, it would bring down the solubility. It would bring down the molar solubility, the X. Ksp is a constant. Ksp is only going to change based on temperature. If I have a different temperature, it's not room temperature, sure, then I have to look up a different value for K. I have to look up a different value for Ksp. But Ksp is only temperature dependent, is a constant. Now, the common ion effect is going to change the X, the molar solubility. Yeah? All right, so that was the first factor, the common ion effect. Are you ready for the next two? So then it's pH and complex ion. Okay, so the next one is pH and solubility. Now for the next two, for the pH and solubility and for complex ion and solubility, I just want you to know the concept. We're not going to do any problems with numbers, nothing numerical, but I just want you to know the overall concept, what would happen to the solubility based on the pH and complex ion. Sounds good? So your textbook is going to go into numbers and doing problems. All I want you guys to know is to know the concept for this part of the class. Now let me show you the concept. Silver cyanide, okay? You look it up in the solubility rules, is insoluble, so we know we have an equilibrium going on and there is a Ksp for it. So far so good? Okay, it's an example. I want you to look at Cn-. What Cn- is, and we've completely ignored this so far, which is okay. This is a conjugate base of HCN, which is a weak acid. So this is a conjugate of HCN, which is a weak acid, right? So HCN, when it loses a hydrogen, then it's Cn-, and then because this is a weak acid, so the conjugate is going to be basic. Remember that, the good old days in acid-base? Okay, good review. So Cn-, we've never thought about this so far when we were doing this Ksp equation, that this is a conjugate of HCN, and HCN is a weak acid, so this is a conjugate base. So far so good? Now, here's what effect it will have. If I add an acid, okay? If we add an acid, then what's going to happen is that the molar solubility, it will increase. And I'll show you why that is and how that works. So here I have this AgCN in solution, right? Is in equilibrium. Some of it will break up, small amount, to Ag plus and Cn-. Okay. Now we just said that Cn- is a conjugate base, right? So if I have an acidic solution, okay, if I have an acidic solution, if I have a solution that has a pH of 7, nothing will happen, nothing at all. But if I have an acidic solution, what's going to happen? Acidic solution is going to have H+, right? Acidic solution is going to have an H+. So what's going to happen if I have an acidic solution? What do you think is going to happen? What's going to happen is that I'm going to form HCN, right? The H+ will grab the Cn because this is basic. I have an acid and is going to form HCN. Okay, let's take a step back. So I have this going on. I have a Cn. I know Cn is a conjugate of HCN. HCN is a weak acid, which means this is a conjugate base. It has a minus charge. We talked about a minus charge. You have extra electrons, so you can act like a base. So this is a conjugate base. Acts like a base. If I have an acidic solution, if I had a neutral pH of 7 solution, carry on. Nothing is going to happen. And this is why we never talked about this until now, because most solutions have a pH of 7. But if I have an acidic solution, that means I have H+. I have an acid, I have a base. Acid-base loves each other, right? Acid-base, fastest reaction in chemistry. So the acid-base are going to come together and it's going to form an HCN. Now, if you form an HCN, pay attention to this. If you form an HCN, what does that mean? So when a CN is formed, H+ will grab it pretty quickly and form HCN. So that means I have less Cn in the solution, because as soon as the CN is formed, the hydrogen is going to grab the CN and is going to make HCN. So this one right here is going to be removed from the equation, because as soon as it's made, H plus will grab it. So the equilibrium is going to shift to the right. Because as soon as CN is formed, H is going to grab it and make HCN. So I have less of this, so it's just going to keep going. So the equilibrium is going to shift to the right. That means the solubility is going to go up. More of these are going to dissolve. Sounds good? This is why when you're trying to clean and you've tried so many things and it doesn't clean, if you have something acidic, like vinegar, that cleans it up pretty well. This is one of the reasons, right? Because acid is going to increase the molar solubility. Because the CN, it grabs the CN, becomes HCN, so you have less of this, so it's going to shift to the right. If it shifts to the right, more of this is going to break down, so the solubility is going to go up. So far, so good? Okay. Hopefully the concept makes sense. Now, here is a crucial side note. The conjugate has to be a conjugate base of a weak acid. Why is that? So, in order for this to happen, the conjugate has to be conjugate of a weak acid. Now, HCN was the conjugate of a weak acid, HCN. Now, why does it have to be a conjugate of a weak acid? Because when you have a weak acid, WA for weak acid, the conjugate is going to be basic, right? If you have a weak acid, you end up having a conjugate that is basic, conjugate base. Now, if you have a strong acid, we've talked about this. If you have a strong acid, what's going to happen to the conjugate? The conjugate is just going to be neutral, right? We've talked about this. If you have a strong acid or base, the conjugate is just going to be neutral. But if you have a weak acid or base, the conjugate is going to be acidic or basic. So here, this is key. This is a huge side note. I'm going to write it as a side note, but it's technically main note. I don't know. Here's a side note. So the conjugate base, for example, here CN was the conjugate base of a weak acid. It has to be the conjugate base of a weak acid, because if you're a conjugate of a strong acid, you're neutral. If you're neutral, H plus is not going to care much about you. If you're basic, the H plus is going to care about you. All right, so far so good. You guys get the concept down? Okay. Do you want to do another practice problem to make sure that you're getting the concept down? Yeah, let's do it. Again, all I want is just concept. If you understand the concept, I don't want to do any math with this. So calcium fluoride, insoluble solid, is going to have an equilibrium. Okay? So far so good? Okay. When I look at this, I want to look at F minus. What can you tell me about the F minus? F minus is a conjugate of hydrofluoric acid. Do you agree? Is hydrofluoric acid a weak acid or strong acid? We talked about this. Is a weak acid. So F minus is a conjugate of a weak acid. If you're a conjugate of a weak acid, what are you? You're a conjugate base, right? Conjugate of a weak acid is a conjugate base. F minus charge and it acts like a base. So conjugate of a weak acid is conjugate base, is basic. So far so good? Okay. Now, pH 7, nothing will happen. But if I happen to have an acidic solution, then what do you think is going to happen? What's going to happen is that H plus is going to go and is going to go grab the F minus. If I have an acidic solution, the H plus is going to go and is going to grab F minus. And if it grabs the F minus, what is it going to be formed? It's going to be forming HF. You follow me so far? Okay, so F minus is a conjugate of a weak acid. If you have a weak acid, the conjugate is going to be basic. It's going to be a conjugate base. If you have a pH of 7, neutral solution, nothing is going to happen. But if you have an acidic solution, that's not the story. What's going to happen? Acidic solution, you have H+. The H+ is going to go and grab the F- because now I have an acid base. Acid loves base. They're going to go and hang out. So I'm going to form HF. Now, if I form HF, what that means is I'm going to have less F- in this equilibrium, because as soon as F- is formed, H is going to grab it. Right? As soon as F- is formed, H is going to grab it. So I have less F-. The equilibrium is going to shift to the right. So it has to make more F-, because F- is now reacted with H+ and it forms HF. So it shifts the reactant towards a product, which means this is going to dissolve more and more and more. Yeah, and that is going to increase the molar solubility. Yeah, again, it's not quantitative. I just want you to know the concept of this. And it's really cool because, let's talk about one more practice problem, yeah? It's very cool because here is where it would impact your daily life. Not your daily life, but this is a real life problem. Statues. What are statues made from? Statues are made from limestone. Did you guys know about that? You probably heard of it. Statues are made from limestone. What limestone is calcium carbonate. It's insoluble in water. So when back in the days people were making statues from limestone, they had a good reason. They said, okay, calcium carbonate is insoluble in water, so let's use calcium carbonate limestone to make a statue. But clearly, they did not take my Chem 1B class, because what they didn't know, they forgot, is that anything that is insoluble in water, yeah, it has some solubility, not much, that's not a problem. The problem is, yes, calcium carbonate insoluble in water, only a small amount would dissolve, except carbonate. What is carbonate? It's a conjugate of a weak acid. So it's a conjugate base because it's a conjugate of a weak acid. So it's a conjugate base. Now, have you guys heard of acid rain? Yeah. Rain is acidic. So when it rains, what happens? Rain has a little bit of H+ in there. So when it rains has a little bit of H+ in there. So then what happens? So when it rains, rain has a little bit of H+ in there. So the H+ is going to go and grab that, and what you end up forming eventually, you're going to end up forming HCO3-, and then if you have more, then carbonic acid. So far so good? Okay. And carbonic acid breaks down into H2O liquid and carbon dioxide. Okay? Again, when you have enough H+, you're going to end up with carbonic acid, which breaks down into water and carbon dioxide. Carbon dioxide is a gas. It's going to go away. There is no way you can make the reaction go backward. So, what's going on here? Statues is happy. People made it from limestone because they said limestone, not very soluble in water. Very true. This is just a very small percentage would break down, except carbonate is a conjugate base of a weak acid. So when it rains has acid in it. It has H+. The H+ is going to go and grab the carbonate. If I have enough H+ going on, I can form carbonic acid. Carbonic acid breaks down into water and carbon dioxide. Carbon dioxide is a gas. It's going to go away. You can't get it back. So what's going to happen? This statue is going to get disfigured over time, because this is going to keep coming out of the equation, and this is going to just keep going that way to form more and more carbonate. So this is going to dissolve more and more and more and more. So the statue is going to get disfigured. That's kind of cool that you know why. Now, there's so many statues that are disfigured, famous old statues, and they have to spend a lot of money to put them back together, all because they didn't take chemistry to realize this was going to happen. So, the take-home message would be, if you get famous one day, and they want to make a statue of you, you're going to say no to calcium carbonate, or you're going to get disfigured, right? So it's going to get disfigured. It's going to say no to calcium carbonate. You say, the best thing to do if they're going to make a statue of you is to make a statue from gold. Gold is pretty good. Gold is not going to get disfigured. Silver is also good, but no calcium carbonate. All right, beautiful, very nice stuff. Now, ready for the very last part? Again, these are conceptual, no math. I'm not going to do any math, so hopefully you're a little bit happy about that. So, what is the next part? The next part, we're going to do complex ion effect on solubility. Complex ion and solubility. Okay. So common ion effect is going to bring the solubility down. If you have a pH, it could bring the solubility up. Now, what happens to the common ion effect on solubility? Okay. Now, first of all, let's go over what is a complex. Let's go over what is a complex. What complex is, it has a transition metal. It has a transition metal, and it has one or more ligands. It has one or more ligands. And I'm going to talk about what a ligand is. Some people call it ligand. I don't know why. It's ligand. Okay? So let me give you an example. Again, these are all conceptual. I'm not going to give you any numeric algebra kind of question. So let me give you an example. Cobalt is a transition metal. Okay? And cobalt is bonded to 6 ligands in here. So a complex contains a transition metal, one or more ligands that are bonded to the transition metal. So here's my transition metal cobalt, and it's surrounded by ligands. So this blue stuff that I drew, those are the ligand. Now the question is, what is a ligand? Let's go over what is a ligand. So again, you know what a complex is. Complex is when you have a transition metal that is surrounded by a bunch of ligands. Now, what's the ligand? Now, here's what ligand is. Ligand is a neutral molecule or anion, it could have a charge, that bonds to the metal through a Lewis acid-base reaction. Now, I almost don't even want you to write this down, because let me explain this to you. So here's the thing. I have a metal ion here, okay? I'm going to have a metal cation as part of the complex ion. And then I have a ligand that is going to be bonded to the transition metal. Okay, so let's go back for a second. So a complex ion is when you have a metal cation and is surrounded by a bunch of ligands. Okay, now metal cation is cation, it has a positive charge. It wants electron badly. Now ligand has electron to give. And that's how they are going to be bonded together. So, complex ion, let's go over this together. You guys got this. You have a transition metal, you have a metal cation. And it's going to be surrounded by ligands. Now, why does this happen? This complexation happen because metal cation wants electron and ligand has electron to give. And ligand has electron to give. You guys are good so far? Okay. Now, let me give you an example of a ligand. For example, NH3. NH3 is a great ligand. Why is that? Let's draw the Lewis structure. Oh yeah, the good old days. Here's the Lewis structure of NH3. It's a neutral ligand Now, why is it a good ligand? Why is it considered a ligand? Because it has lone pair. So it has lone pair to donate. Because remember the whole idea, the metal cation wants electron. The ligand has to have electron to give. Does ammonia have electron to give? It does. So it's a ligand. Okay. So let me give you an example. So this is my ligand. Ammonia is a ligand. So let me give you an example of a complex ion, right? Let me give you an example of complex ion. It would be cobalt with 6 ammonia around it. And then here is the charge for the entire complex. This one right here, this is a charge for the entire complex. Okay, so I had before, I have a cobalt here, and then if NH3 is my ligand, it's going to be surrounded by 6 ammonia. And now you don't have to have all the same ligands. You can also have different types of ligand. It could have like 2 ammonia and then 2 water and then 2 F minus. It doesn't have to all to be the same ligand. So the transition metal is surrounded by ligand. It could be 1 or more different types of ligand. It doesn't have to all be the same. So far so good. Okay, so this is an idea of a ligand and a complex ion. So what this is a complex ion. You guys are good so far? And again, this is the charge of +3. Now, let me give you another example. Let's see, I have silver metal cation, and then I'm going to have 2 Cn minus. Okay, they are going to make a complex because Ag plus is a metal cation. Cn minus is a ligand because it has a minus charge, right? It has electron to donate. And then, so silver is going to be surrounded by 2 Cn ligands. So far so good. Now, how did I know that Ag was going to get 2 Cn ligands and not be surrounded by 6 ligands? You wouldn't know until I tell you. I will tell you what the ligands are and how many you need. Okay? Now, I wanted to show you this, but I wanted to show you where I got this number from. Silver is +1. Cn is -1. 1 + 1, 2 - 1. So the charge over here is what? The overall charge over here is -1. Do you agree? +1, -2, -1. Now the charge over here has to match that. Remember, the charges have to match on both sides. So the overall complex has a -1 charge. The overall complex has a -1 charge. You guys are good so far? Okay. Now the last problem, the cobalt had a +3 charge. And it had 6 ammonia, which is a neutral. So I ended up getting cobalt, 6 ammonia, +3. Because again, here it had a +3 charge. This is all neutral. So here I have to have a +3 charge. So the charges would match up. Yeah, you guys feeling pretty good about this? Okay. You probably want to do one more practice problem before we go over this. Okay? Yeah, let's do it. So, we do this too. Let's do one more. Let's do to zinc +2. That's a metal cation. And then it's going to have 4 hydroxide around it. Hydroxide is a ligand. So again, I'm going to write this down. So this is my metal cation. That's how I compliment my metal cation. My metal cation. And this is my ligand. Minus charge. Oxygen has a lot of electrons to give. Okay, it's a good ligand. So the ligand has electron to give. The metal cation wants electron. Metal cation is plus charge, wants electron. Ligand here has electrons to give. So they are going to form a complex ion. It would be zinc. And I told you it's 4 of them. So it would be zinc hydroxide. Now, what would be the overall charge? Let's go over it together. On this side, I have 1 + 2 and 4 - 1 plus 2 and 4 minus, so it will be minus 2 the overall here. So the other one has to match the other side. So it would be zinc hydroxide for minus 2. So far so good? Okay. So that was not the whole point of this part, but I wanted to make sure you know what a complex ion is. I want to make sure you know what a complex ion is. So complex ion is when you have a transition metal, is a metal cation, because metals are usually cation, they lose electron, become positively charged, and it's going to be bonded to a bunch of ligands. It could be 1 ligand, 2 ligand, 4 ligand, 10 ligand. You don't know. I don't know. We don't know until we go to lab and see how many ligands would a cation accept. So I would tell you how many ligands would be bonded to the metal. Okay, so ligand, because ligand has extra electrons to give. So in this case, zinc likes to have 4 ligands. So here I'm going to have my complex ion, and I'll show you how the charge works. Yeah? Okay. Now, let's go over how would this affect solubility. Let's go over how this would affect solubility. You guys are doing really good, by the way. Hang in there. We're almost there. AgCl. Insoluble solid, Ag plus and Cl minus. So far, so good. Okay. Now, nothing will happen if I just have AgCl in water. Nothing will happen if I just have AgCl in water. Okay? If I have AgCl in water, nothing will happen. Now, what if I have this AgCl, which has a Ksp, and I have a solution, this is in water, and AgCl is in ammonia and water. So in water is not going to make any difference. We've done the Ksp before. Now, what if I have AgCl in an ammonia solution? Ammonia is a ligand. Ammonia is a ligand. So what's going to happen is that the ammonia is going to go and grab the Ag plus and make a complex ion. So the ammonia is going to go and grab the Ag plus and is going to make a complex ion. Now here's what I want you to know. If the ammonia goes and grabs the Ag plus and makes a complex ion, that means again the Ag is going to be out of the equation. So what do you think is going to happen to the solubility? The solubility is going to shift to the right. So the solubility is going to increase. So far so good? Okay. So again, here's the only thing I want you to know about this. I'm not going to give you any problem. I just want you to know that, again, when you have an insoluble salt in a solution, it has a Ksp going on in water, we're good, nothing is going to happen. But if you have it in a solution that could make a complex ion, the ligand is going to go and grab the metal ion. If the ligand goes and grabs the metal ion to make a complex ion, to form a complex ion, that means this is going to be out of the equation. If this is out of the equation, then the equation has to shift to the right to make more of Ag. So what happens to the solubility? The molar solubility is going to increase. The molar solubility is going to increase. So far, so good? Okay. All right. So what I want to do now, let's quickly wrap up what we talked about. What we talked about, we talked about that there's 3 things that could affect molar solubility, yeah? The first one is common ion effect. And if you have one of the common ions, that's going to make the solubility to go down. So far, so good? Okay. And we already knew that, because let's say if I have Ma going to M plus and A minus, you already knew this, because if I have one of these common ions, that means if I have one of these common ions in the solution, it would have to shift to the left to adjust the equilibrium. So I would have more of this solid and less of the ions. So the solubility will go down. So common ion, you already knew that one. You're good with that one. The other one is the pH. We said the pH would increase the solubility. But again, remember, this is only the case if you have a conjugate base of a weak acid, right? If you have a weak acid that has a conjugate base of it, If you're in an acidic solution, if you're in a neutral solution, nothing will happen. If you're in an acidic solution, yeah, the pH is going to make the solubility to go up. So far, so good. And the last one is complex ion. Yeah, if you have a ligand in the solution, again, the ligand is going to grab the metal cation, and what's going to happen is going to make a complex ion, and that's going to make the solubility to go up. For these two, what did I do that for? For these two, I just want you to know the concept that if you have a conjugate base of a weak acid in an acidic solution, the solubility is going to go up. If you have a ligand in the solution, the ligand is going to make a complex ion with a metal cation, and the solubility is also going to go up. All right, beautiful. This was a heavy lecture, I know, but you guys got this down. Again, for the pH in complex ion, I will just ask you something conceptual. We're not going to do the numbers. Yeah? All right. Beautiful job. Really nice job. Thanks for hanging in there with me. I will talk to you guys next time.